Recent satellite observations indicate that the Earth's global energy imbalance grew by nearly half a watt per square meter per decade between 2003 and 2024, an acceleration largely driven by a significant decline in low-level cloud cover. This trend highlights a persistent challenge in climate science. Clouds are the primary thermostat of our planet, yet they remain the largest source of uncertainty in every major climate model. Understanding why this sunscreen effect is thinning requires us to look at the atmosphere not just as a global system, but as a series of isolated vertical experiments.
The difficulty lies in the scale. A global climate model might divide the world into grid squares roughly 100 kilometers wide, but an individual cloud forms and dissipates across a few meters in a matter of seconds. To bridge that gap, we use what's known as a single column model, or SCM. Think of it as a vertical slice of the atmosphere, a single straw poked through the layers from the ground to the edge of space. By focusing on this one-dimensional column, we can simulate the physics of clouds and radiation with intense precision without the overwhelming computational noise of a full 3D global simulation.
It seems counterintuitive to simplify something so vast into a single dimension. If you're stripping away the horizontal movement of air, the wind blowing from a mountain to the sea, don't you lose the very dynamics that create clouds in the first place?
You do lose the horizontal context, which is why SCMs are essentially used as laboratories. We prescribe the horizontal winds based on real-world observations or larger models, then let the SCM calculate the vertical physics. A prime example is the MIT single-column model. It functions like a diagnostic bridge. Instead of guessing how a square of the Pacific Ocean will respond to warming, we take a specific vertical profile and apply rigorous thermodynamic laws to see how heat and moisture move up and down. This allows us to isolate specific variables, like how a change in aerosol concentration affects the brightness of a cloud top, without having to simulate the entire planet's weather at the same time.
If we look at the internal architecture of something like the MIT model, it's not just one big equation, it's built from specialized modules. How do these distinct parts interact to represent something as fluid as a cloud?
It relies on three core physical engines. First, there's the radiative transfer module, often using the Morcret model. This tracks how solar energy enters and exits the column across the entire electromagnetic spectrum, even accounting for how ozone absorbs ultraviolet light. Second is the cumulus convection scheme. This is based on foundational work by Kerry Emanuel, and it's responsible for the life of the cloud. It distinguishes between those gentle, fair-weather shallow cumulus clouds and the violent storm-producing cumulonimbus towers. It calculates how much latent heat is released as water vapor turns into liquid, which is the engine that drives vertical air movement.
And the third piece would be the moisture distribution itself, because clouds aren't just there or not there, they have varying thickness and liquid content.
Exactly. That's the layer cloud parameterization, often credited to researchers like Sandrine Boney. It translates raw humidity data into a statistical distribution of cloud fractions. It tells the model what percentage of that straw is filled with cloud and how much liquid water is actually in there. This is vital because the relationship between humidity and cloud formation is incredibly nuanced. If a layer hits a specific saturation threshold, the model triggers internal mechanisms to calculate condensation and precipitation, creating a realistic hydrological loop within that single column.
This modular approach seems to provide a controlled environment, but the real world isn't controlled. In June 2026, we're seeing these low cloud decks over the Pacific and Atlantic Oceans retreating. If the models are so precise at the column level, why is there still such a massive spread in our global projections?
The spread comes from how these localized processes aggregate. In the latest reports from 2026, including studies published in Atmospheric Chemistry and Physics, we're finding that while models capture the general physics, they often suffer from a too few, too bright bias. Satellites like NASA's EarthCare, which launched recently to specifically address this, reveal that models tend to produce fewer clouds than actually exist, but they make those few clouds much more reflective than they are in reality. These errors sometimes cancel each other out to give a roughly correct energy balance, but for the wrong physical reasons. That's a dangerous foundation for long-term climate prediction.
So we have a situation where the models might be getting the right answer by accident. How does the single column model help fix a systemic bias like the too few, too bright problem?
It acts as a testing ground for hypotheses. For instance, there's the mixing desiccation hypothesis. The idea is that as clouds rise, they force drier air from above down into the lower cloud layer, which effectively dries out the cloud and causes it to dissipate. This decreases the overall cloud cover and allows more sunlight to hit the ocean. Testing this in a full global model is nearly impossible because there are too many variables. But in an SCM, we can isolate that specific mixing process, compare it to aircraft data from campaigns like NASA's Activate, and see if the math holds up. We can literally tune the convection scheme in the column until it matches what we see in the real North Atlantic.
That aircraft data sounds essential. You mentioned Activate, where they use synchronized flights, one plane flying through the cloud and another above it. What are they finding that the models are missing?
They're finding that the transition from a solid, overcast cloud deck to those broken, cotton ball cumulus clouds is much more sensitive to aerosols than we thought. Aerosols, tiny particles like dust, salt, or pollution, act as seeds for cloud droplets. If you have more aerosols, you get more smaller droplets, which makes the cloud brighter. But these smaller droplets are also less likely to fall as rain, which can actually make the cloud last longer. This is the aerosol-cloud interaction, and current research from the University of Edinburgh in 2026 suggests that almost all climate models systematically underestimate how much cloud cover responds to these aerosol changes.
This brings us to the concept of cloud feedback. If the planet warms and that warming causes low clouds to disappear, that's a positive feedback loop. The warming creates a condition that leads to even more warming. How certain are we about the strength of that loop right now?
According to the most recent 2026 assessments by CEPI and others, the low cloud feedback is estimated at roughly 0.39 watts per square meter per Kelvin. That sounds like a small number, but it accounts for about 40% of the observed trend in solar radiation absorption. It's the leading driver. The uncertainty used to be whether clouds would help us or hurt us. Now, the consensus is shifting toward them hurting us by thinning out as temperatures rise. The question now is exactly how fast that thinning happens. This is where the MIT model's ability to simulate vertical stabilization is so critical. As the surface warms, it changes the vertical temperature gradient, which can cap the clouds and prevent them from developing.
Is there a limit to what a one-dimensional model can tell us? At some point, the fact that weather moves sideways has to be the dominant factor, right?
Absolutely. An SEM can't tell you where a hurricane will go, but it can tell you if the physics inside that hurricane's wall, the way it releases latent heat, is being calculated correctly. In 2026, we're seeing a push toward kilometer-scale global models. These are incredibly high-resolution simulations that try to do what the SCM does, but everywhere at once. The problem is they are so computationally expensive that we can only run them for short periods. So we use the SCM to perfect the physics of a single column. Then we apply those perfected rules to the massive global models. It's a way of ensuring that when we do run those billion-dollar simulations, the underlying assumptions about cloud droplets and ice crystals are physically sound.
We've focused a lot on low clouds, but what about the high-altitude ice clouds, the cirrus clouds? They have the opposite effect, don't they? They trap heat like a blanket.
Exactly, and they are even harder to study because they're made of ice crystals, not liquid drops. The shape of those crystals, whether they are plates, needles, or columns, changes how they scatter light. Models often struggle with the ice-liquid balance. A study from NASA's Goddard Institute in early 2026 pointed out that many models produce too many high-altitude ice clouds. This traps too much infrared heat. By using SCMs coupled with new LiDAR data from the EarthCare satellite, scientists can observe the vertical profile of these ice clouds with unprecedented accuracy. EarthCare uses an atmospheric LiDAR that can actually see the thin layers of aerosols and ice that previous satellites missed.
It feels like we're in a golden age of atmospheric observation, yet the data is revealing a more urgent situation than we expected. The fact that temperatures are rising faster than many models predicted suggests that the sunscreen, these low clouds, is failing more quickly than the math accounted for.
That is the prevailing concern in the 2026 literature. The loss of reflective cloud cover, especially over the dark ocean waters, means the Earth is absorbing more energy than ever before. It's not just about CO2 trapping heat anymore, it's about the planet's natural cooling systems being compromised. Single-column models allow us to deconstruct this disaster in slow motion. We can take a broken model that isn't matching satellite data, put it into a single column, and figure out exactly which module is failing. Is it the way we calculate evaporation? Is it the way we handle the transition from liquid to ice? This diagnostic clarity is the only way we can reduce the tenths of a degree uncertainty that makes the difference between a manageable future and a catastrophic one.
It sounds like these models are more than just simulations. They're the bridge between the microscopic world of a water droplet and the macroscopic reality of a changing planet. If we can't get the physics of a single column of air right, we have no hope of predicting the fate of the entire atmosphere.
That's precisely it. The MIT single-column model and its peers provide the specialized environment where radiative, convective, and cloud-based physics interact in a way we can actually control and understand. By validating these interactions in a one-dimensional space, we identify the systematic errors that would otherwise stay hidden in the complexity of a global model. As we look at the data coming in for the rest of 2026, these tools are what will allow us to turn uncertainty into actionable insight. They bridge the gap between local observations and global survival.
The precision of a single column reveals the immense complexity of our climate's balancing act. If you found this breakdown of atmospheric physics insightful, share this episode with someone who follows climate science. It's a direct way to spread a better understanding of the tools shaping our future.